Okay, so here goes. Question 5 is asking you to look at a couple examples and determine which of the three chi-squared tests you can use. The three tests are goodness of fit, homogeneity, and I'm going to struggle with saying that word, so forgive me, independence as well. The question that is being asked for each is a little different, and if you understand the question, then you will be able to build on that. In the case of a goodness of fit test, you're looking at an observed distribution and wanting to see if it's consistent with an expectation. For instance, if you expect that the zodiac signs are randomly distributed, you would expect that if you have a bunch of CEOs, you would expect even amounts in all 12 zodiac signs. That's the expectation. And then, so what we're looking at, the number of groups in this case would be one group. There's just one variable. The one group, CEOs, the variable, zodiac signs. And you're looking to see if the zodiac signs are evenly distributed, because that is what is sort of expected. Homogeneity, we are looking to see, are the distributions of the variables the same in the two or more populations? So we can have two or more populations and there's one variable. So that's what makes it a homogeneity chi-squared test. Example of that, if you want to compare the distribution of zodiac signs of CEOs, so the one variable is zodiac signs. The groups are CEOs, professors, athletes. You're looking at the zodiac signs for all three, which is your one variable, and wanting to see, is it the same breakdown within the three groups? So it's several groups, one variable, and you want to see how that variable differs, how the breakdown of that variable differs among the two or more groups. Alright? So the important thing for homogeneity, it has to be two or more groups and it has to be only one variable. Now independence, the question that is being answered is there evidence of an association between the variables? Now there's one group, two variables, and you want to see if there is association of the two variables. For instance, if you ask the zodiac sign and ask if people are left-handed or right-handed, that's one group of persons. We're asked two different measures. What's your zodiac sign and are you left or right-handed? Then we're going to try and see if there's evidence of an association between zodiac signs and being left-handed or right-handed. This is essentially the summary of the questions and how they will split into the three chi-squared tests that you will have. Now a little more details on each. The goodness of fit test, and this slide or these slides that will continue here are the exact slides from the textbook. So goodness of fit test, you're given the following: the count of items in each of several categories, and you have a model that predicts the distribution of the relative frequency. So the question naturally arises, does the actual distribution differ from the model because of random error, or do the differences mean that the model does not fit the data? In other words, how good is the fit? Hence goodness of fit. So you have a model and you want to see if it fits the model. An example that's here, you have stock market up days. This is the historical data, so this is what we have seen when we count thousands of days. We see this ratio of up days. Now in a sample of 1,000 up days, this is what we are getting. Now we want to know if this is the same as this. So up days appear to be more common than expected on certain days, especially on Fridays. This is higher than this. The null hypothesis is that the distribution of up days is no different from the population distribution, and you can test the hypothesis with a chi-squared goodness of fit model, and you can do it because you have one group, one variable, and you want to see if it matches the expectation. Alright, conditions for that, the count data condition, the data must be counts for the categorical variables. Independence, the count should be independent of each other. Think about whether this is reasonable. Randomization condition, the counted individuals should be a random sample of the population. So based on the information given, you will know if this is true or if these are true. Goodness of fit, assumptions continued. Sample size, there must be large enough data so that you can check the following. The expected frequency must be at least 5 individuals per cell. Alright, so another example for goodness of fit is a credit card company has silver, gold, and platinum cards, and they expect the ratio to be 60, 30, and 10. Now, what type of test would you use for this? It would be a goodness of fit. What would be your expected value? It's going to be the ratio 60 to 30 to 10. So if you sample this many persons, then you would have expected 60% of it to be silver, 30% to be gold, and 10% to be platinum. Now you have to make sure that you're translating the expectation from percentages to actual figures. Alright, this is just a detail of that. Now the chi-square test for homogeneity, and let's just go back real quick. What we're looking for, we have several groups and there's one variable. For instance, we're comparing the distribution of zodiac signs in CEOs, professors, and athletes. So the distributions, we want to see if they are the same. So what we have here, we have people from different countries responding to a question that is being asked about the importance of appearance, and then we're wanting to see if there's similarity between the groups. So we want to see if the different groups are homogeneous. That is sort of what we are looking for, and you must have a basis for judging the homogeneity. In this case, it is the response to this question here that was put in the form of 1 to 7 as a response to importance of appearance. And broken down, this is what you will see. So the ratio of the 7s for the different groups is shown there graphically, and you can see that, hey, this seems different, but obviously we have to use a chi-square test to really do the scientific assessment and not just a visual to say, hey, that looks big, so the groups could not be homogeneous. Alright, so our null hypothesis is going to be that the relative distribution, the relative frequency distributions are the same. That is, the groups are homogeneous. And the chi-square test will perform the mathematical analysis on that. Alright. The assumptions for chi-square test for homogeneity. The count data must be counted, must be independent, must be random, sample size must match, must be enough data so that you can check the following condition, which is expect at least 5 individuals per cell, and this is based on your expectation. So a real simple example, if you expect it to be 10% for 10 groups and you only sample 20 persons, 10% of 20 is going to be 2, so your expected value for each cell is going to be 2, so you would need more data in that case. So you want to make sure your expected data for each is at least 5. So chi-square test for homogeneity continues here with another example, and you can take a look at this in the slide. What we have is 3 different cards, and then the mailing list are located here. You want to see if these are homogeneous. So in other words, is the ratio of mailing 1 to 2 to 3 the same for the different types of card. Now that's sort of the qualitative aspect of the homogeneity test. Chi-square test for independence. Let's remind ourselves what we're looking for. We are looking for one group with two variables, for example zodiac signs, and if people are left-handed or right-handed, to see if there's a relationship. Is there evidence of an association between the two variables? So what's happening here? The two variables are the age range for the persons who responded, and we have their thoughts on the importance of appearance, and we want to see if these two are independent. Are the age and appearance independent, or is there a relationship? And that is the breakdown in the form of a graph. And then what we're saying with the chi-squared test, we're looking for independence. Chi-squared test for independence, the test is mechanically equivalent to the test for homogeneity, but with some differences in how we think about the data and the results. In the homogeneity test, there's one variable, which is appearance, and is measured on two or more population. In the independence test, there are two variables, age and appearance, and we're measuring it on a single population. So it can be, the difference can be subtle, but try and think through it and you will come up with the correct answer. We ask the questions, are the variables independent rather than are the groups homogeneous? So the subtle distinction is extremely important. With the independence test, you're looking to see if the variables age and appearance, are these independent, as opposed to looking at appearance breakdown in multiple groups, which is the homogeneity test. Alright, so it requires a little wrapping your head around it, but there's no other way to do it than to go through and think of examples and try to assess to see if they fit the model that is there. And again, it all comes back to this first table here that shows the breakdown. Alright? It's been a little long, but I wanted to make sure that we spoke through enough examples for you to start to get the gist of it. Alright, thank you.